So my AP class the other day, AP, if you're on here, this is for you. We've been doing that Softato lab forever, and whenever we first started talking about electricity, you know, we talked about how electricity really doesn't flow that fast, and you guys were like, well, how does it get there? And I kept trying to tell you it was like this idea of a potential difference, and I didn't want to get into it. And you guys were like, no, but the thing, and I was like, please no. And you were like, but the thing, and I was like, please no. And, but the thing. So we're going to talk about that. We are going to talk about the thing, and we're going to get really in depth into how electrons are flowing in the wire. I don't like doing this because it is, and I'm not even kidding you, what I ended up doing to do this properly is, as I brighten myself, I am looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pages. 12 pages. I'm looking at 12 pages in this book here. It's actually a pretty good book. It's Physics for Scientists and Engineers, A Strategic Approach, the 4th edition by Randall D. Knight. It took 12 pages in this book just to get Ohm's law, V equals IR. Yeah, 12 pages. And I think that's just silly because, you know, normally when we think about circuitry and Ohm's law, we're not really concerning ourselves with individual number of particles going through things. So we're just kind of looking at the circuit itself. But y'all wanted to know how this all works, so we're going to do it. Okay? I'm going to be here a while. We're going to start like this. Y'all asked for this. We're looking at how electricity flows. I don't have time to cover this in class. There's just too much stuff. But we're going to look at it. Okay? Okay. We talked about in class how if I have some very long wire, okay, the individual electrons in the wire can be moving very, very, very quickly. But the drift speed, which we'll just call VD for a drift speed or a drift velocity, it's very low. Like, we're talking on the order of a few centimeter per hour, if that. Okay, it's like super low. And you guys kept asking, well, then how does all the stuff move? How do we get electricity to go so fast? So it has to do with the fact that even though these electrons, as a bulk sense, are moving very slowly, individually they're whipping around super, super fast. Okay? And, you know, even if this is a very thin piece of copper line, there are a lot of electrons in here. Like 10 to the 13th easily, probably more if we, you know, work out the math, which we will in a little bit. There's a ton in there. Okay, just a ton of them. So they're all going to bump in real quick, and all the information is going to carry extremely fast. Okay, but we're going to call this VD a drift speed. We're also going to call just little I here. This is going to be a current for us. Okay, and we're going to call it an electron current because traditionally, remember, current is a positive current. We're looking at things in a positive direction. They're positive charges moving, even though you can't move positive charges like protons along the line. You'd be, you know, exploding your wire along the way or something. But we're going to look at this electron current and imagine that these electrons are running down the line. Okay? So let's get 12 pages in. let's pretend that we want to see how many electrons are passing through this cross-sectional area. So we've got a bunch of electrons here, and there's some cross-sectional area here that they're all passing through. Okay, yay, we're electrons. We can also almost imagine this is like a, a pseudo-Gaussian surface, but let's just imagine it's a cross-sectional area. Okay, the number of electrons passing through that area then is the current multiplied by the time, because remember, an electron current that we have here, the easiest way to think of it is simply the number of electrons per second that we have. So if we have number of electrons per second times seconds, the time, we get number of electrons. Okay? So this right here is the number of electrons passing through some cross-sectional area in some amount of time. It's just your current multiplied by that time interval, whatever that time interval may be. More precisely, we could call it like a delta t because it's an interval, but whatever. Okay. Now, if we want to go a little bit further than that, as these electrons are traveling from this point to some next cross-sectional area, they are traveling some distance delta x. Okay. So we're traveling some delta x here. If we wanted to figure out what that delta x would be, we could simply say that delta x would equal the drift velocity multiplied by some change in time. And interestingly enough, the number of electrons coming through are probably going to be the same amount coming out the backside, because we can kind of think of this as a fluid moving through, and we'll do this later this year, such that those times are the same. Okay? Because of this, what we can then end up doing is we could imagine that if we have some number density of electrons, okay? So this is a number density. If we have a number density of electrons here, then what we could look at with this is we can say, okay, the number of electrons passing through this distance or this space in time, this volume, so to speak, because if this has a cross-sectional area, which is like meters squared, and this is a length, meters, we see that we've just built ourselves a nice little cylinder here, okay? And that cylinder has some volume, and this is the number density of our electrons in that volume. So since our volume of this entire setup is cross-sectional area times delta x, and if our number density, where do I want to write this? If our total number of electrons here is equal to the number density times a volume, which is A delta x, and I can relate delta x to this down here, I can now say that the number of electrons passing through a point is equal to a number density times a cross-sectional area times how fast the drift velocity of electrons are moving times some change in time. Whew! That's how many electrons are passing a point. That was a lot just to get to that. Okay? But y'all asked for this, so we're doing it. This means then that if we take the number of electrons and a time, like we divided out time here, the number of electrons divided by some amount of time, isn't this just that, the current? So we can actually say that the current we have here, the electron current, is equal to the density of the electrons times the cross-sectional area of the wire times the drift velocity, which is very low. Okay. Oh. We all cool with that so far? Okay. this actually has some interesting things when we look at it. This implies that if you have a larger cross-sectional area, the charges can flow easier. You're getting more charges through them, which will increase your current. It allows the charges to move easier. Okay? If you have a smaller cross-sectional area, it's harder for those charges to move. So that's just an idea that we have right there as well. Okay? Now, if we think about the idea of trying to create some current, okay, we need to generate some sort of push on the electrons. And the easiest way to do that is to set up an electric field. Because we've talked about all through our statics units that if I have a parallel plate, positive and negative, if I put in the electric fields go positive, negative. Oh, look at this edge effect. Positive, negative, uniform, positive, negative, uniform, positive, negative, uniform, edge effect. Okay? And we know that a positively charged particle is going to go along the field lines while a negatively charged particle is going to work against them. Okay, we've talked about that in class. When we have a circuit, such as a 9-volt battery, and that means over here we're at 0 volts, that is the same similar idea as just a parallel plate. This side could be 9 volts, this side 0 volts, high to low voltage. So what we're essentially doing for a battery like this is we are creating, in the wire, so to speak, an electric field. Now, you can't create an electric field in the wire. That's a bad idea because that's a conductor, and you don't have the electric field in the conductor. But that's basically the idea of what we're doing there. There's this internal electric field that we're kind of creating through this potential difference. Now, this is how a positive charge would go here, and technically when we talk about the electrons, our electrons are moving backwards. And we're only talking about the electrons here because you guys wanted to talk about them with this kind of weird setup. We're never going to talk about the electrons. We're always going with this positively charged article. Okay? So, let's imagine for a second that... How do I want to do this? We need to move these electrons down the pipe, or backwards through the pipe, I guess. I don't know, it's such a weird way of thinking about it because I never think about it like that. Let's make the long wire again. Okay. Make a bunch of positively charged particles, negatively charged particles, whatever. Okay. You've got a bunch of particles in here. They're everywhere. These particles are all darting around. And they're darting around, we can assume, randomly. Totally random. Okay? When these particles are bouncing around, they are going to have a collision with another particle. Okay? They're going to have a collision somewhere. There's a huge number density. Electrons are going to bump into some electron at some point in time. When this happens, this could happen in any of our three-dimensional regions, the X, Y, or Z axis, okay? But in theory, since it's happening in perfect randomness, in theory, the amount happening in the X direction should be the same amount as the Y, should be the same amount as the Z. So we should have a pretty uniform distribution on how all these particles are colliding. I mean, there's hundreds of millions of billions of them. There's tons of them. So, given that it's random, we're going to say everything's equal. So we're going to say, English. We're going to say that if we do this for the X direction, just moving left and right, like I have this written out here, it'll apply for everywhere else, okay? When these particles collide, there's a force there, and thereby an acceleration. So the acceleration that these particle feels in the X direction, and remember this could be Y, this could be Z, is equal to a force divided by a mass. F equals ma. We just divided m over, okay? if we think about our electric charges and our statics, F is equal to QE, or this would be over M. If we're speaking directly about electrons here, that Q is the electron over the mass of the electron. Okay? So that's what we have there. When they hit, there is an acceleration, change direction due to this collision. Okay? Now, let's also assume that because there is some electric field going on here, all these electrons here, which are going to go opposite of the electric field, are going to continue to accelerate over time. Okay? So this acceleration here, we can think of it as collisions, but we can also think of it as this electric field is speeding it up. Okay? So the best way to think about it is the E field speeds up electrons by this amount. Okay? If we wanted to find the velocity of any of our electrons, we could say the velocity in the x direction, simply because we're going in the x direction, is equal to some initial x velocity plus an acceleration in the x direction, which is really this, times some change in time. Okay? If we do that substitution, we see that it's Vix plus E, oh, that's a weird thing to write. I haven't written that in so long, over M times some amount of time. Okay? That equals our x velocity at any point in time. Okay? Now, if we take a look at the average electron's velocity due to the electric field, okay? Remember, the average velocity an electron could have moving through this electric field as it's moving through it is this drift velocity, okay? And we're going to say that this drift velocity is the average. Now, note here, I drew an arrow because it's a vector. Here, I draw this line as it is an average, okay? That's an average there. It's like a mean. It's like a stats move. That average x velocity is equal to the average initial velocity in the x direction that these electrons will have plus the acceleration that they feel and the average amount of time that they feel this acceleration. Okay, so that is what the drift velocity actually is. You have electrons sitting in this wire that are being acted on by this electric field. They're all acting in random directions, but the average in a certain direction is found, and then it's also increasing based off of some acceleration. Okay? That's like such a terrible thought to even think of that. But that's what we're looking at. Okay? From here, things get a little strange. Okay? We are going to state that this quantity, delta T, it's the average time between collisions. Okay? Because as these particles are accelerating through this electric field, they can accelerate so far, and then boop, they hit an electron, and they got to bounce somewhere else. And then they get back into the x direction again, and they boop, boop, boop. And all of them are doing this. So they're getting a little far, and then they're bouncing in some random way. Okay? This is also kind of the idea of a random walk, but it's a little different. They're getting so far and then bouncing. And they're only able to travel like this for some time of delta T. since delta t is this time between collisions, let's come up with a specific variable for it. We are going to label it tau. Okay? This is the mean time, or t, between collisions. Okay? That's what we're looking at there. With this, taking this idea of the mean time between collisions and working it up here, what we can really do with it is this EE over m delta t. We could really write it as replacing this delta t with a tau, okay? And this tau, it is more of a property of the conductor we're acting through than anything else. Okay, it has to deal with kind of like how big the conductor is, what is it made out of, what's its density. So that tau is kind of a fixed term, so to speak, which means that we can say that this drift velocity is equal to the electric charge, and I'm going to write tau within here because it's kind of a constant, and that's a constant, and the mass of an electron is constant, times the electric field. Okay, so really the drift velocity we have is based off of an electric field. Tau has to deal with the substance itself. This here, though, gets to go all the way back up into this. So let's draw the big, see that right there? See that right there? This means that our electric current, the number of electrons per some amount of time, remember that, is equal to the electron number density in a wire times the electric charge times the mean time between collisions, tau, times a cross-sectional area all over the mass of an electron times an electric field. All of this right here, constant based off of the density, constant because it's electron, constant based off of your object, cross-sectional area is a constant because you cut the wire, mass of the electron is a constant. This is your only possibly changing value, and that value changes due to a voltage. Okay? So we've got a bunch of constants dealing with our wire, and then E dealing with a voltage. Okay? So that's something to think about there as well. Not only this, but if you wanted to, if you reworked this equation, you could see that the mean time between collisions could be found simply by taking mass of the electron, if you knew the drift velocity, divided by EE. This is approximately on the order of 10 to the negative 4 meters per second. So you could find an average value for tau. This right here is the number of collisions per second. Okay. The collision rate is 1 over tau because that gives you seconds per collision. Okay, so kind of a sidebar there, but interesting thing as well. Okay. Okay, so we're back to this here. We're looking at the current. The electron current is equal to some constant based on our wire times an electric field. Okay. Now, if we kind of take a tangent here, we talked about this in class. A current, traditional current, going through a wire, or just in general, is the number of some charges, an electric or positive charge, divided by some amount of time. Okay? Now, this charge that we're moving through, these number of electrons, have some sort of charge associated with them. That's like a charge per time. okay, because each of these has some amount of coulombs associated with it. If we wanted to, we could break this down into its differential piece and say that in general this is some change in charge in some change in time. Okay, so we get a tiny bit of charge and a tiny bit of time going through the current, because if we once again draw the wire and have our tiny cross-sectional area, there is some tiny bit of charge going through this and some bit of time. We've called that a current. Okay, so that's all we did there. We've seen that. This also means that Q is equal to the current times some amount of time. Okay? Now, if we kind of look at this here and we look at that jump bringing us to this point, we also kind of think of this as well, then what we're really looking at down here is that the current, well, if this is the number of electrons and this is the charge, well, we can get that just by saying this is really the electric charge by the number of electrons or whatever moving in, okay? So this is technically an electric charge in an amount of time, and that gives us Q over T, which is dQ by dt, okay? Now, not only this, but this current going through our system then, if it is charge in time, and that's how we've defined the current going through our system, this right here, this is, we've already defined that. And this is where things get annoying. And remember how I said some books like to use a capital I? This is why. The current going through our system is equal to some electric charge, normally for an electron, if we're thinking about this electron drift and the electron's actually moving, NE over T, we've already defined that way up here. NE over T is this electron current, remember? Where did I even put that? It's right here. This is the electron current. So the current going through our system is equal to the electric charge times the electron current. And that just makes things confusing, right? But it's okay. This allows us to basically understand that we are talking about current in terms of electrons, but we're pushing it through a positive way. This I here is opposite of this electron current as well. Okay, so that's the idea there. Now, if I equals E, IE, and for IE, we know what that equals all the way up here, NVAVD, and what we can do there is we can simply say that this here is equal to wrong marker, wrong pen. We can say equal to N, the number density of the electron, times E for the electron times the drift velocity times A. Just taking this quantity right here and subbing it down. So we just have an extra E term that we've bopped in through the middle, okay? This is the idea of a current. Now, if I don't just want a current, if I want a current density, like how much current do I have passing through some cross-sectional area at once, well, I have a current. If I need it per area, there's my area. So we can say that the current divided by area is a current density, and this current density would just be equal to N E by the drift velocity. Okay? This is a current density. This current density, this is easy to find. Simply because we can get current really easily. And we can get A by just measuring it. I spelled measuring wrong. It's too late. So if this is easy to find, this is measuring, and I know the charge of an electron, and I know a general idea of what a number density for my electron should be, I can easily find the drift velocity based off of this current density. And that's why we kind of use the current density there. Whew. Okay. But wait, there's more, Mr. Botzer. Jeez, really? Okay. You asked for it. Remember all the way up here? Y'all asked for this. Okay. We just covered current density. So, what can I do with the current density? Well, a current density is equal to NE E VD. We know what VD is. This is a term that we've defined in its own sequential breakdown. We've got NE E, and then this VD here was equal to the term E tau over M times the electric field. So I'm just going to combine this and say NE E. I don't want to put that minus there anymore. I'm no longer going to put the minus. It's going to make things weird. Squared. See, I don't want it to be minus 2. It's squared. Tau over M electric field. Ugh. Once again, these are all some constants of the system. The electric field is what can change here. Okay? Now, if this is a current density, or how much current is moving along through our wire through some opening, what this is representing right here is how easy it is to, or what's the ability of the wire to push this charge along, okay? This right here is a conductivity. Okay, it's how conductive the wire actually is. That is what that is measuring. We will give it the term sigma. So what we also have here is that our current density is equal to our conductivity, sigma, times our electric field. Okay? Now, while conductivity is how easily an object is able to move along its electric charges, we in class have been looking at the resistivity, which is just the opposite. It's how resistive something is to allow charges to flow along it. Resistivity uses the letter rho. It is equal to 1 over the conductivity sigma, which means it is equal to the flip of it, m over NE E squared tau. But this is weird because that is the resistivity. I mean, we've worked out a ton of math to show that, but in class, through our Softy-Dough lab, you weren't measuring tau. You weren't measuring the mass of the electron. You weren't measuring the number density of your Softy-Dough. You were looking in terms of resistance, length, and cross-sectional area. So, how does that get whipped into here? Okay? Let's imagine this. Let us imagine that we have some electric field. Okay? If you think back to chapter 17, one of the things we talked about with the electric field is that it is the derivative of the potential field. Okay, dV by dr, or some people call this ds, some distance. Okay? This means, if we kind of take this into the more, like, we can measure it sense, this is, or it leads us to, rather, in terms of a magnitude, in terms of a size, some change in voltage over some distance, some change in distance, okay? And we just use the magnitude here, the size. That's why the negative goes away. That's all we're really concerned about. This, in general, is some voltage drop over some path length. We're going to call it L. It's a length, okay? Now, if up here, where is it? We've defined the current of our wire per some amount of surface area, cross-sectional surface area, equals a current density, J, then that means this I is equal to JA. So what we can say is that the current in our wire, I, is equal to the current density times a cross-sectional area. Okay? This means, because we know what J is also equal to, J is equal to sigma E, the conductivity times the electric field, times A then, which we could rewrite this, if we so chose to, as being AE, and instead of writing this in terms of conductivity, we would write it over rho, because see, rho is equal to 1 over sigma, which means sigma is equal to 1 over rho, okay? So I just replaced the sigma with the rho in the denominator. That's the current. We also know that if we look at this equation here, and we look at this right here, this is the electric field. So we can go on to say that the current is equal to A over rho, that's what's already there, times some voltage difference over L. There's the A and L that we've been looking for. There's rho, okay? Now, if I divide out L over here, if I say if I divide V out, I over V equals A over rho L, I have this. But if I simply flip all of this or do a sweet cross multiplication kind of thing, I'll see that rho L over A equals V over I. This term right here, V over I, that term is equal to the resistance in our circuit, okay? Because we have some resistivity by the length of the wire divided by a cross-sectional area. That is what this is actually saying. This right here is the long way to get Ohm's law. We, in the end, just state this. This is Ohm's law. It came about because all the way at the beginning, y'all asked for this, we were thinking about how electrons were moving. What was the current of the electrons? How many did we get moving through some sort of surface in some amount of time? How fast were they moving? What was the density of that? And then looking at our old electric field idea and how we can move through here, how are they accelerating? How long were they accelerating before they hit another electron and kind of bounced off their path? We kept moving through these ideas, combining these equations, looking deeper into the equations, looking more into the fundamental properties of our conductor itself, looking at the current of our system. And remember, this is the current of like the system itself. This is the system itself. This is what we've eventually called big I, because it's all of the charges moving through that point. And we started looking at it in terms of coulombs, in terms of a charge, not just in terms of a number going through. And then once we did that, we got some current density. We worked into our ideas of conductivity, flipped it for resistivity, got some idea of a resistance with voltages, and then boom. That right there is a resistance, as we've seen in our lab. Rho L over A equals equals the resistance, which, once again, like I said, is Ohm's law. Okay? Because technically, this all equals V over I. I personally don't like writing it R equals V over I. I've personally always been a fan of writing it V equals IR. And because I hate writing capital I's, I always write this just as IR. But note, some books don't like to write it like this because of this small confusion of, do you mean this current or do you mean this current? And we're never talking about the electron current. We did all of this work once a long time ago so that we never had to deal with it again. And we could just think of it as positive charges moving. Okay? So keep that in mind. That is the idea of how the electrons are actually moving in the system and what is actually happening. Okay? You're having a bunch of tiny electrons move very quickly. They can only move a small distance before they hit another electron to pass that information. So the information is passed very quickly. But in the end, we end up getting Ohm's law back, which is really the only thing we care about. Okay? So that's that idea. Just as a quick thing, because I don't think we actually solved it as I was kind of going through this. Where is our tau? Average values of tau. Average values of tau are on the order of like 10 to the minus 14 seconds, by the way. So you're looking at like 0.1 femtoseconds. That's how short tau is. So the electrons don't get very far, but they're really moving quickly in that conductor in order to hit as often as they do. Okay? That also means if you flip that for your collision rate, on average we get something that's like times 10 to the 13 to 14 collisions per second. Oh, did I mess this up? I think I messed this up. Oh, I did. This should be seconds per collision. Apologies. And these are collisions per second. Okay? Whoops. I thought that felt weird when I was writing it originally, but I messed up. Okay? I'll put a little air up there. Yeah, sorry I made that little air there. I was moving kind of quick for this. It took 42 minutes in order to get all that. Okay. Either way, this video is done. Don't ask me that question ever again. It's a crazy question. Well, it's not a crazy question. It's a really good question. It's just one I hate answering because, like I said, it just goes on and on and on. You have to talk about these electrons, and we don't talk about the electrons. We think about it as a positive charge pumping through. Okay? So, we're done with that. Finn. Is anybody even in the chat anymore? No. Nobody's in the chat. Okay. Either way, cool stuff. I'm gonna get off. I've been on for an hour and 15, so I'll leave you all with this. Whoa, it's quadratic time. Whoa, it's quadratic